Hi, everyone again. Yeah, I'll be talking about a sublinear time algorithm and lower bounds for matching size in the non-adaptive query model. Uh, yeah, so I'm currently a postdoc at Birmingham for people who don't know. But this work was done when I was at Waterloo. So let's start with uh, something simple, like one of the words in the title. What is a matching? So you're given a graph, and the matching is just a bunch of edges such that no two edges share an endpoint. Right, so here orange you can see a matching of size 2, and this is the largest possible matching, called the maximum matching of size 3. Right? So I want to start with a puzzle, not so much of a puzzle, but this is going to show up in our problem today. So you're given a graph, it's a bipartite graph with n vertices on both sides, and you're given a matching of size n. Okay. Also, you know that every vertex on the left has degree square root n exactly. And the question is, there's this algorithm alg that samples a random edge incident of every vertex. And yeah, the question is, what is the largest size matching I can find in expectation in the worst case? Right? Algorithm is very simple. For every vertex, you just sample one random. Right? So I'm sure some people see it, but I'm just going to give people 2 seconds to think about it. And someone can probably answer. And in the talk, we don't care about constant factors. So we don't care about constant factors generally in the number of queries here, but also today in the approximation factors, since we'll be looking at large factors, we don't care about number like constant factors there as well. So anyone want to tell me roughly what is the size of the matching you will see? I will see. Okay, I can tell you guys that it's square root n. And why? Because every vertex has square root n neighbors. So you're sampling one edge. So the probability you sample the special edge is 1 over root n. And so you get a matching of size root n. And this is the best you can do, sort of, right? So if I add the root n and this subset, they go to this red portion here. I might see the entire red portion, which is root n. But outside it, I will see at most root n more edges of the matching, right? So yeah, root n is really the right answer. And these are the kind of sampling things we're going to use in our upper bound and a little bit in the lower bound as well. All right, so this is just to give you a flavor. And now let me start with the plan for the talk. So we look at some previous work on matching, then we'll talk about our results. Then we'll go into a simple upper bound, a slightly not simple lower bound. And then if I have time, I will also go into some of the details of how the lower bound is formalized using a coupling algorithm. Okay. So let's talk about some classical results. What do we know about matching? So Edmonds gave the first polynomial time algorithm for non-bipartite maximum matching. And this was later improved to running time n times root n, right? And this was done in till 1980, but we still don't know a better bound than this, right? So improving beyond n root n is a major open problem. But no, this is for general graphs. For bipartite graphs, we know we can do better. So the result for max flow tells us that, oh, max flow can be solved in m to 1 plus log of 1 time. And again, m is the number of edges in the graph, and n is the number of vertices. So this implies that bipartite matching can also be solved with n to the 1 plus log. And this algorithm is not combinatorial. So there was also a combinatorial algorithm that is almost linear time for dense graphs. Okay. So all of these are exact algorithms. What do we know about approximations? And approximation algorithms are faster, right? So you can get a linear time algorithm, which gives you a true approximation. This is just a simple greedy algorithm. And you can also get a 1% epsilon approximation in M over epsilon. All right. So the question is, are we done here? We've gone all the way to linear time. And I would like to say no, because we have sublinear time as well, right? So this is what this talk is going to be about. So let me try motivating sublinear time algorithms a little bit. So today we live in this world with massive graphs, and a lot of you have seen these pictures already, but there are two people who haven't. So we have papers and citations, web pages and hyperlinks, social networks and friendship links. And with all these massive graphs, it's hard to even read the entire input. Right? So if the graph is stored on disk, for example, random access queries become expensive. And so classical algorithms fail to address some of these challenges posed by massive graphs. And so we're going to use sublinear time algorithms uh, to fix this. And why? Because you're going to use only few random access queries. Okay. So let me define the model we're going to use today. So you want to approximately solve the problem faster than reading the entire input, right? And so you have the adjacency list access model, which we're going to use today, where you have degree and neighbor queries. So over here, let's say this is a graph you have. Initially, you don't see any edges. And then I can ask the adjacency list, which is empty currently. What is the first neighbor of A? What is the second neighbor of A? And then you start seeing edges. And then you can also ask for the degree of T. All right. So what do you know about matching in this sublinear time model, right? Unfortunately, you can't do anything. If you want a constant approximation for matching, it needs n square queries, right? So you essentially have to look at the entire graph, even if you want a constant approximation. And this gets slightly worse, that this low amount goes in both adjacency list and matrix models, right? So you can't do much if you want to output the matching. But if you saw the title carefully, out of the 100 words, there was one word that said, oh, we're going to look at matching size. And there's some hope, which is for matching size, we can estimate the size in sublinear time. All right. So what do we know about matching size? So Vihan gave a two approximation algorithm in O tilde n queries, and the tilde n is hiding polylog factors in n. So in n polylog n queries, you can actually get a two approximation to the size of the maximum matching. And you can also get a 1 minus epsilon approximation in rate of n square time. Okay. Okay, so these are sort of improvements on the approximation algorithms we saw previously. And there is significant work over here, right? We know tons and tons of results. But one thing about all of these results is that they relied on adaptive querying strategies. Right? So what does this mean? The algorithm will ask some queries, look at the answers, and based on the answers, ask more queries. So it is very natural to ask what happens if my queries are not adaptive, right? So in the non-adaptive model, you fix all queries in advance, ask them together, and you get all the answers. And so the question is, okay, what can you do over here? And yeah, nothing was known about this. And non-adaptive queries have been studied in other models like property testing and even recently in local computational algorithms. So this is a national direction to explore. And what we show is that there are strong lower bounds against these non-adaptive algorithms. Right? So we say that getting polylog approximations is hard in O-line queries. You need n to the 1.5 queries for that. Okay? Things get even worse. If you want to get a polynomial approximation, roughly even an n to the 1 over 3 approximation to the size of the matching, you need more than O-line queries. You cannot do it in n polynomial queries. But I mean, then now it looks like, okay, maybe you cannot do anything in this model, right? Maybe this model is too restrictive. And I want to say, no, that is not the case. You have an algorithm that gives you a square root and upper bound in O-line. Okay? And we also show some general trade-offs that for some n to the delta approximation, you get some trade-off for the lower bound and for the upper bounds. But for today, we'll be thinking of just n polylog queries and trying to see what are the best approximations. So I'd like to pause here and ask if there are any questions up to this point before we dive into the proofs. No. So, like the Hardensons, we have breaks set under the 1.5 queries. And yeah, I don't know what you can do above n to the 1.5 in the non-adaptive world for these large approximations. Yeah. Right. So, okay. So if you want to get a 1 minus so there is a low on the adaptive world that says if you want to get a 1 minus epsilon approximation, you need n raised to 2 minus f of epsilon queries. Yeah. Yeah, we don't know. Just because you mentioned difficult. What's a 1 minus epsilon approximation? Good. So, like for matching size, if your matching size is, let's say, n for k, let's say, then you want to output something which is 1 minus epsilon k or lambda. Between 1 minus epsilon times k. These ones here. Good. Yes. So, you're right. I should say a 1 plus epsilon approximation because I want approximation factors to be larger than 1. So when I say n to the delta approximation, I mean between the matching size, whatever k, and k divided by n to the delta. Yeah. So yeah, you're right. Like usually people say for matching, since it's a maximizing problem, people say 1 minus epsilon approximation. But I think it's easier to just say n to the delta instead of n to the minus delta. It has to be the matching size, so they could overshoot as well. Yes, they could overshoot. But yeah, we're saying that okay, that's always and there's also a simple trick. If you know you between these bounds, you just define thing by object overshooting. That should always be done. Okay. Johnny, do you have a question?
I'm just thinking through what's going to happen if you would tell us how plus some epsilon. See, you have n to the 1 over 3 there, and epsilon 5. But there's also a constant. Sorry. But I think you get to the gap.
Right. Yeah, and there is a significant gap, right? So n to the 1 over 3 roughly versus square root n. So we don't know what happens in the middle. Okay, so let's start with the upper bound. The algorithm is extremely simple. Okay, so we're going to look at again the special case of getting an order square root n approximation in order the n queries. And the algorithm for every vertex, it samples one random edge, the exact algorithm we saw in the puzzle, and outputs looks at the maximum matching in the sampled graph and outputs this size. That's it. Okay. And note that I'm saying, oh, we're sampling random edges, but that was not allowed because we can only say, give me the ith neighbor, for example, we cannot say give me a random number, but that's okay. You can use an order and blow up. Why? Just guess the degree and then do the sampling. So this is not a problem. So we'll assume at random at samples as well, like random neighbor samples. Then. Okay. And okay, the query complexity, the number of queries we're asking is clearly n times polylog n, right? One random max over x times maybe the log n blow. And also if you're saying, maximum matching takes a lot of time, I'm going to say, okay, we can, instead of running outputting the size of the maximum matching, we can just output the size of the greedy matching. And since we're dealing with such large approximation factors, we're just going to lose a factor 2 over here. And so it's okay. Right, so we're going to get something that's fast in time as well. So sublinear time, out in time. So let's see how this algorithm gives you a square root approximation. Right. So let m star be a fixed maximum matching. And we call the vertex of m star low degree if it has degree less than 4 times square root. Otherwise, it is high degree. And we're going to break the proof into two cases. One, where a constant fraction of the vertices are low degree, and another where a constant fraction of the vertices are high degree. In the low degree case, many m star will actually be sampled, and this is exactly the puzzle, right? Up to this constant of 4. And in the high degree case, since the vertices are high degree, the property of sampling an unmatched neighbor is going to be right, and that's why you can grow the matching. So let's go over both of these. So I've just written down the proof for the puzzle again, but it's just okay. What is the probability I'm going to get this matched edge? It's 1 over like 4 times root n. And so I have n edges, and so I'm going to get something which is of m star by square root n times some constant. Right? And so this gives us a root n approximation. This makes sense, right? Good. Now, the other case is slightly trickier. When you have many high degree vertices, what happens? Okay, so firstly, if we have a matching of size square root n, we're done. Right? And what I mean is in the sample edges, if I see a matching of size square root n, I can just say that the answer is square root n and I'm done. Because the optimal matching cannot have size more than n. Right? And so square root n is always a good approximation. So now I can say that, okay, if I reach square root n, I'm done. But what happens before I reach square root n? And here I will say I'm going to make a lot of progress. Why? Because let's look at this picture. Let's look at this vertex B, which is high degree. Okay, so it has 4 times root n number of neighbors. But I've not reached a matching of size square root n in my samples yet. And you should think of going one by one over the samples and trying to apply this argument. And I want to say, if I've not reached square root n size, the number of matched vertices is at most 2 times square root n. Okay? So what is the probability of picking an edge to an unmatched vertex? It's half. Right? So I'm going to grow the size of the matching by 1 at every step with probability half. And so I get even a constant approximation here, right? If like if we have a lot of high degree vertices and we're very far away from square root n, then like we've not reached square root n, then you can even get a constant approximation, which is definitely a square root n approximation. Okay, any questions here? Okay. So yeah, in both cases, we get a square root approximation and we're done. Right? So this concludes the upper bound. What about the lower bound? So let's talk about that. So here I want to prove this lower bound that says that for some n to the delta approximation, I need n to the 1 plus epsilon queries. Then for simplicity, let's set epsilon and delta equals to 0.1. This is not going to lie on the trade-off curve, but it's just calculation. So let's simplify things and say epsilon and delta are just 0.1. Okay. So to prove the randomized lower bound, what we're going to do is prove a distributional lower bound. And like this is pretty common, right? I will prove a lower bound against deterministic algorithms but for distributions. And this will give me the randomized lower bound by Yau's min-max. So what is our distribution? We have a yes distribution that has a matching of size at least n. And just a small note here that n is like not exactly the number of vertices, it's a constant times the number of vertices. So yeah. And in the no case, the matching size is going to be only 0.9. And so there's a huge gap between the matchings in the yes and the no case. But we'll say that if we fix a deterministic algorithm alg that makes only n to the 1.1 queries, it will not be able to tell apart these two distributions. Right? So what I'm going to give alg is this hard distribution, which is half times ds plus half times d no. And this just means with property half, I'll give you a random sample from yes, and with property half, I'll give you a random sample from no. And I'll say I cannot distinguish between these distributions with probability more than half plus little of 1. Okay. All right. So let's look at what the distributions are. Right. So here we have three groups of vertices, two groups of vertices, sorry. You have these A vertices here and these B vertices here. And in the yes case, you have this large matching, which is of size n. And in the no case, you just have edges between like AL and BR and AL and BL. Right? Note the sizes of AR and AL are just n to the 0.9. And so AL and AR form a vertex tower. And so the matching size is just going to be n to the 0.9. Right? Like basically all the once all the vertices in AL and AR are matched, we don't have any other edges left to match. Okay. And so yeah, basically there are n vertices here and n vertices here, and the same over here in like over here and here as well. And over here at the top, how are these edges arranged? These n edges are basically n to the 0.1 matchings, each of size n to the 0.9. So you add a bunch of perfect matchings between these guys here. And for the no case, you'll just add a perfect matching between AN and maybe the first n to the 0.9 vertices here, and then AN, the second n to the 0.9, and so on. So you keep adding a bunch of matchings between A and B. And this is just going to be the same thing. N to the 0.1 matching is beside in this. Okay. One final thing here is the edges I'm drawn in blue are fixed. And that means there's always going to be an edge from the first vertex here to the first vertex here and so on. And the edges are drawn in green and pink, those are random matchings, right? So the number of possible yes instances is basically this. How many ever n to the 0.1 matchings, like the number of possible ways you can do this. And I'll make the number of no instances the same as well. And it's going to be this as well. So I'm going to put random matchings over here and fixed matchings. I mean, this is not too important. It is just to make the number of yes and number of no instances the same. Okay. Now, does anyone see a problem with this? Sorry? Very good. Okay. But that is getting slightly okay. So if I look at the degree of a vertex here and degree of a vertex here, it's still the same. Right? Like these guys have degree 1 and these guys also have degree 1. And these guys have a higher degree. Is there a simple way I can tell these two distributions apart? Can you circle around the vertex? what was the sample adaptive vertex? Yeah, I know is a named like let's say 1 through n or something. So I think
Yeah, you could sample adaptive vertex.
Yeah.
With some probability in this B1 or B2. Then you can check whether its neighbor has the P1. But you check if the sample vertex is P1. Check if the neighbor.
Exactly. Very good.
So yes.
Yeah, exactly. And even something more simple, the algorithm add it like that, we just makes one random sample per vertex. It will see the entire matching. Like it's going to see a matching of size n, and you can easily tell the two distributions apart, right? Just like if you make the random sample on this vertex, you will see this do it. And so to hide this information, we're going to add what I call a bunch of dummy vertices. And you should think of this as almost a bi-clique between the left side and the right side here. Like between these guys and these guys, there's an edge with probability roughly half. And now what is going to happen is if you make a bunch of samples over here, very likely that it's going to go inside the code, inside this dummy. Right, so now you won't be able to use Vihan, for example, your algorithm, or even this algorithm of sampling random neighbors. Because if you just sample one random neighbor per vertex, earlier you saw a matching of size n, but now you're just going to see a matching of size n to the 0.1.
So it's like complete.
Almost like every edge you add with probability half, something like that. Right? So when making queries, you can think of it as a complete. So when you make a query with probability roughly 1 over degree, it's going to be like with probability 1 over degree, it's going to be here, and the degree is roughly n to the 0.8. Right, so the probability you get something in the code is just 1 over n to the 0.8. Okay. All right. So if you make degree queries, then you can easily separate out these vertices from these vertices. Why? Because these guys have degree n to the 0.9-ish, and these guys will have degree roughly theta n, right? Because for a vertex here, there are n edges, n vertices here, and it has order n edges to that. But what you cannot do is sort of separate out A and B vertices by looking at that. So, at, just because the number of degree in the code for these two kind of vertices is slightly different, I'll make that total degree the exact same. Right? You just have to adjust how many edges I add from here to B. So for B vertices, I will add B star minus 1 because it just has one edge in the code. And for these guys, A guys, I'll add B star minus 10 to the 0. So everyone in this box has degree B star, which is roughly n to the 0.9, by exactly n to the 0.9, which is roughly n to the 0.9. Okay. So now by degree queries, you cannot tell these guys apart. And if you want to distinguish between them, you can make n queries. And can someone tell me why, if I make n queries on a vertex, I can tell whether it belongs to A or belongs to B?
Or
The degrees are exactly the same. I'm setting B star to be the degree of all these vertices in A and B. So if you make degree queries, you always see n to the 0.9 by 2. But I'm saying if you make n queries, I can still tell these guys apart on a vertex. And maybe what I should also tell you is you should always assume that you can separate out A vertices, A and B vertices from B vertices. Because let's say you're going to query everything, all the vertices degree. And so all the vertices with degree D star, you will say this is in the code. All the vertices that are not D star, like more, you'll say this is not in the code. So let's say you know this already. Now I'm saying on a vertex you make n queries.
the first instance, the graph is this one. Right? Second instance.
So in both, you're sort of disconnected because here it's like this component and this component, there's no way to go between. Yeah, if you just look at the code, I'm saying, but okay, were you saying
The entire
oh, yeah, like everyone is heavily connected to the board. No, like from the top, AN, I can go to DR, and from DR, I can go to
oh, it's not just clear the set, clear is both clear.
okay. Yeah, so sorry. Yeah, okay. Actually, uh, it is this end, and the top graph is connected, right? Because the bottom graph, every time you take, like there are no edges that
What is the nature of DR is connected to everyone or?
everyone on the left.
So including here and here.
Mhm.
That is fine. And after the ground is fine.
Yeah, sorry. Yeah, sorry. Fine. Yeah. Yeah. Good. All right. But do you see why if you make n queries on a vertex, you can say whether it's A or B? Exactly. Perfect. You look at all the neighbors you get, you see how many of them are in the core and how many of them are in the dummy, right? Because you know, like from the first point, you can separate these out because you look at their degrees and you're like, this guy has only one low degree vertex and many high degree vertices. It has to be in B, right? Yeah. So just assume that after you make the queries, the adversary also tells you, like you also get to know which vertices are in the box, which vertices are not in the box, right? That you can just tell by degree. Okay. So my point is, on a vertex, if you make a lot of queries, you can actually tell whether it's A or whether it's B. And so, or maybe the clicker stopped working. I can continue from here. Sorry, just give me 1 minute. I'll try to connect it again. Okay, on the side. Thank you. Okay, so I'm saying if you sample a lot of vertices on both sides and start making n queries, you start seeing these edges in the core, and basically you reveal both of their endpoints. And as soon as I reveal both endpoints, like for example, something like this, if I know there is an edge with both endpoints that are A, I'm done. Right? And no, this has to be in this case. There are no A edges in this case. But I would say this never happens when you just make n to the 1.1. Right? So the way to think about this now is like the goal of the algorithm is to see an A edge or a BB edge or an AB edge. As soon as it does, it's game over. You know if you're in the yes case or if you're in the no, right? And I want to say that that is something that will never happen. And to say that, I'm going to formalize it by saying the following. I'm going to say that ALG sees a disjoint unit of stars in the core with hyper. And what that means is, when the algorithm ALG makes the queries, what it'll see will look like this. So it'll see an A vertex, and it knows this guy is an A vertex. Because it'll see a bunch of neighbors in the core, right? But for all of these, which I call petals, so this is the star center and these are petals, and like yes, my star has petals, but when you see this, you will not know whether this guy is an A vertex or a B vertex. And so you're like, oh, maybe I can be in the yes case, maybe I'm in the no case. I have no idea. So does this make sense? Like two things here. One is that what is the lemma trying to say? And the second thing is, if the lemma is true, why the algorithm cannot really tell apart the two cases. Right? Hopefully, this intuitively it makes sense. And if I don't know if these are A or B, then I don't know whether I'm coming from yes or no. Okay. All right. And why do we see stars? And this is the reason we introduced the dummy, right? Because most of my queries are actually going to the dummy. So for this vertex, if I get lucky and I see some neighbors in the code, for these vertices, I will not get lucky and I won't see anything. We will formalize this, but yeah. And also, I'm adding directed edges. So for this vertex, if I queried, made queries on it and found this edge, I'm going to direct it out of it. And so what is this lemma saying? It's saying that you only see stars. That means you don't see any three paths. Right? You see only two paths. You don't see any three paths, but it's saying more. You don't see any two paths that look like this. So for this vertex, I discover a neighbor, and for this vertex, I discover a neighbor. You don't see something like this. And this is a star in where the arrows go outward. So you cannot have a star where the arrows go inward. Right? So that is also not allowed. Okay. And let's see why this is true. So we're going to prove this level now. All right. So let's start with one important thing, which is the labels of the vertices. So if the algorithm sees that, oh, this guy's A1, this guy's A2, this is B1, then it can easily distinguish between the yes and no cases. Why? Because it will just make queries, n queries on B1 and see if it has an edge to B1R. Right? So make queries on B1 and figure out if it has an edge to B1. So we have to hide these names from the algorithm. And so what we're going to do is going to add a random permutation of labels on the left and the right. Right? So when I show this instance to the algorithm, I will tell it the names A1, A2, and so on. I will give it some random names. So use on the left side, A1, A1, B1, A2.
And you assuming that I just see this model?
Yes.
Yes, we have it. But just to confirm how the sublinear algorithm works, we have like the entire code. So is that we just like ask for the names and just say zero?
Yeah. Not 0, 1. So this is not a matrix where you can just say where the edge is there. So what I ask for you for what actually can be the ith neighbor.
Copy the service.
Yeah. Yeah. So what the algorithm will see, it will see that there are these vertices called U1, U2, and so on, and V1, V2, and so on the right. Okay. This is what the algorithm does. And so what the algorithm is going to do, it's deterministic, right? So it's going to say for every vertex V, I'm going to fix QV number of queries, right? And this QV can be anywhere between 0 and n. So I can say, for this vertex V, I'm going to make n queries. For these guys, maybe one query. But because of this random labeling, notice what happens for an underlying vertex. Right? So if I just focus my attention on A1, what is happening? Since the permutation is random, in expectation, A1L just sees n to the 0.1 pairs. Right? Because it's going to get a random label from this side. Right? And for each of them, I've made some number of queries here, but the total number of queries I've made is n to the 1.1. And so if you average it over the n-ish vertices, then you will see only n to the 0.1 queries on an underlying node. Does this make sense? Right? And so for like the calculations, it's okay to think of just making n to the 0.1 queries on an underlying vertex, like A1 or B1, for example. Okay. So now I'm going to tell you what a happy vertex is, and it's the same as a star centered. I just don't know that I'm going to see a bunch of stars yet, so I'm going to call it a happy vertex. But a happy vertex just finds an edge in the code, right? So what is the probability this A over here is a happy vertex? I'm just union bounding over the number of queries I make. And the probability when you make one query, it's just the number of core edges divided by the degree. Right? So the number of core edges is just n to the 0.1 at most over here. And the degree is just n to the 0.9. Okay, by 2, but we don't care about constants. And union bound over just n to the 0.1 pairs. So the probability that a vertex is happy is very small. And the probability that there are two fixed vertices, one on the left, one on the right, they're both happy, is even smaller. And so if I just union bound over all the edges, right? So I want to look at an edge and say, what is the probability that this is happy and this is happy? Right? So both of them discover neighbors in the code. That I'm saying is just the glow of that. And this will give you the size, right? Because I know there is no vertex, no pair over here, which has an edge between them. And for both endpoints, I will see something in the code. And so this tells me I have a union of stars. Right? Because I cannot get something like this. If both of these, if this is an edge, both of these cannot be. And okay, the stars may not be disjoint. So I have to do a similar calculation for these, what I call happy wedges. But it's just like the same calculation, the constants are slightly different, but I'm going to say this also does not happen. And I'm basically going to get a disjoint union. Any questions with what happens here? You don't have to follow the calculation completely, but intuitively, I'm saying that the probability that two vertices here, both of them discover something in the code, is very small. So I'm really not going to see like an edge where both endpoints are happy. So I see a bunch of stars. And so if I know this endpoint of this edge is happy and is a star center now, then I will know that this guy has no edges found in the code. So I really don't know if it's an A vertex or a B vertex. Okay. All right. Yeah. So we know where the star centers at A and B, but we don't know if the petals are A. Yeah, of course.
It's a big jump to say we can assume that we just spend it with 0.1 queries per
Uh-huh.
just the fact that it didn't work. Because it breaks down if I make n queries on one vertex and everything else gets into so crazy.
Right. So what's going to happen there if you make n queries on one vertex? So you're going to make n queries on this label U1 that you see. So across all instances, what's going to happen is maybe in the first you'll you get all neighbors of A1. In the other instance, you're going to get all neighbors of A2 and so on. Right. Wait, that makes sense. Sorry.
So I just missed the last part. So you're saying like assume the one that I get is call it A1.
Yeah, so I'm saying if you make n queries on some vertex B, then because the permutation is random, it's not that you're going to see n queries made on a particular underlying vertex all the time, right? So that's going to change. And what I can do is like that was just sort of to give intuition, but now over here, I can do this calculation as well. What is the probability that a fixed edge is happy or not? And I'm saying when you make this n queries on a vertex, maybe in one vertex, one time it's going to go to A1, but over this randomness, a lot of the time it's not going to go over A1, it's going to go to these other ends. So the probability, like this statement, the probability, or even just this statement, the probability A is happy, right? So fix this vertex here is going to be like the one. Because once I look at that vertex, it's like, oh, what is the probability that that vertex you made n queries on lands on A itself? Because it is random, so it can land anywhere else. And then maybe yeah, we can all, yeah. So I mean, the way I've done it is just to simplify some calculations. But if you do this expectation calculation, like how you're saying, yeah, so you will still end up with the same. Okay. Yeah, that's a good question. All right. But yeah, the point here is now let's just believe we have the disjoint union of stars. And so I know the star centers are A or B, but I don't know if these petals are A or B. Right? And this is what's going to tell me intuitively that, oh, we don't know if it's in yes or no. But this is not the information, the only information the algorithm gets. The algorithm is also going to see edges to D, right? And maybe it can use this intuition, maybe it can use this extra information to distinguish the cases. So we need to formalize this algorithm. And what do I mean by this? For example, for a vertex, if I see its degree -2 edges to D, okay, then I will know for sure that this has to be a B vertex, right? Because the difference in the number of D edges between these two guys is like n to the 0.1. Right? So for a vertex, if I see a lot of edges going to D, then I'll be like, maybe it's a B vertex and not an A vertex. Right? Because if it was an A vertex, maybe after making so many queries on it, I would have seen something over here and not here. Right? So the algorithm can do crazy things. It can maybe it doesn't just give up once it sees this. Right? So this intuition that we have that the algorithm cannot do anything once it sees the stars, we just need to formalize it. And this is where the coupling argument comes in. Okay? So what is the coupling argument saying? It's going to say that we can formally show that the probability of success of this algorithm is just half plus the log. Right? So it can't do much. It cannot distinguish with probability 2 over 3. Okay. So this is what the picture looks like. So over here, I've drawn all the no instances. So every node in this graph is a no instance, and every node in this graph is a yes instance. And when Al makes all its queries, it's going to see some observed graph, right? It's going to see something. And since Al does not make a lot of queries, let's look at this observed graph called GOBS1. There are multiple different no instances that give you the same observed graph, right? Maybe there are two instances that just differ in one edge. I will see the same, I will see the same observed graph for them, right? And now I will also see the same observed graph in the yes as well, right? So yeah, so what we saw is that the core is going to look exactly the same with high probability, like you're going to see this disjoint union of stars. And if you set the petals to be like A, then you're in the yes case. If you set them to be B, you're in the no case. But basically, you have a sort of correspondence between the yes and no cases. So what I'm going to do in this, I'm going to draw an edge from this guy to this guy. So between these two nodes, if the observed graph is exactly the same under the queries the algorithm makes. Okay. So for this first observed graph, I made these edges, and what this sort of arrow over here is indicating is that all edges will go from an observed graph to the same observed graph on the right. It cannot go this way, right? Because in that case, the algorithm is seeing two different things. So I can't say that those sort of equivalent or something. So this edge means that for this instance and for this instance, the algorithm sees exactly the same thing.
You're doing like complete almost splits,
Yeah. And now I'm saying that I will get I get a perfect matching between the left and right. Okay. And this is slightly far from the truth, and we get to it. But basically, this is what the coupling ideally would like to say, you know. Note that over here a node is not only the graph from the instance, but it has all the information. It is the graph from the distribution. Also, how adjacency lists are permuted. For the same graph, I can have many different permutations of the adjacency list, right? And also the labels we give to the vertices. So the U's and the V's that we have. But okay, you don't have to worry much about it. Basically, I'm saying look at all the information the algorithm sees, and we're defining a node based on all of this.
It's not clear that the sizes are the same, right?
So the sizes are the same because the way we constructed the hard distributions, we had n to the 0.1 matchings of size n to 0.9. So the number of yes instances and the number of no instances we had was exactly the same.
Each block,
Each, sorry.
like G ops one
Ah,
is the same size as
very good. Yeah, that's true. It doesn't have to be the same. So here is the next picture, but they're not the same. Here the block size is 3 and here the block size is 4. So like Vihan said, the blocks are not going to be the same on both sides. So you cannot add a perfect matching, right? But I'm saying I will not add a perfect matching. I'll add a matching of 1 minus little of 1 fraction. And this is now true. This I can actually do. Okay. And what do you do? If there are 3 guys here and 4 guys here, just match them arbitrarily. Over here, there are 4, here 3, just arbitrarily. This is 3, 3, we're lucky. So you don't get a perfect matching. So let's turn it into a perfect matching by adding this red edge that goes between observed graph 2 and observed graph 1. And red here is bad because these edges are distinguishable. The algorithm can easily tell these two apart because the graphs look different, right? This is 1 and this is 2. But and these blue edges are good because the graphs are identical on both sides. And now the question is, okay, why are we doing all this? And the reason is that there's an equivalent way of sampling this hard distribution. Right? So what does the hard distribution say? With probably half sample from yes, with probably half sample from no. What I'm going to do is pick a random edge over here and then pick a random endpoint. And I want to say this is the same distribution as this distribution. Right? And the distribution is essentially uniform over all the nodes, right? So this is going to give you the same. Pick a random edge and pick a random endpoint. And now this tells you why I cannot succeed. Because what is the success probability of ALG? If it picks a blue edge, ALG is doomed. It cannot tell whether I'm coming from the left or coming from the right. So the success probability there is just half. It can do guess. That's it. Okay, for the red edges, it can succeed with probability 1, but there are very few red edges. It's little of 1. And so the success probability of ALG is just half plus little of 1. And this is why ALG cannot succeed. Does this make sense? Yeah. So that's something we have to show. So we have to show that the number of blue edges is a large fraction, 1 minus sigma of 1 fraction. And so the red edges will be small. Okay. And yeah, I'm just going to conclude very quickly. So this is the goal. And it is hard to prove that these, okay. So what we want to prove is that if you look at graph, observe graph 1 here on left and right, its sizes are close to each other. And if we can show that for all the observed graphs, we will get what we want. We will get this large matching. But if you fix an observed graph on the left, how many nodes does it contain? Like, this is not an easy question. Like I don't know how to figure out how many nodes it contains. And it's, in fact, it depends on which observed graph you fix, right? So if you say that, oh, okay, you want to just count the number of nodes on the left and right, it does not seem that easy to do. But what you can do is the following. So we'll fix the randomness step by step. So what we do is, okay, let's look at all these like nodes that we have over here. Let's fix some of the edges that are part of the observed graph, right? So we know Alg makes these particular queries, so we can fix some of the edges of the graph that Alg sees, and then we can and that partitions the number of these instances into these boxes. Then let's look at the first box. We can also maybe fix some of the labels, right? So the labeling is basically a permutation. We fix the permutation. So we maybe see, so now this box gets divided into multiple parts. And then maybe we also fix some part of the adjacency lists. And once we do all these fixings, we end up at this observed graph. And now I have this particular observed graph in my hand, and I know what part of the randomness I've fixed and what part I've not fixed. And so I will know exactly how many nodes are there inside. Just because for the remaining randomness, I can set it however I want, and the observed graph is not going to change. Because essentially everything the algorithm is queried for those locations, I've fixed what I wanted. Okay. And once we do this for the no guys, we also do the same in parallel for the yes guys, so that we end up at the same observed graph. And once we do this, all we have to do is compare how many nodes do you have in this observed graph in X, and the same observed graph you end up in Y, in X and Y. And now it's easier to show them within 1% of function. Okay. All right. So I'll just skip the summary and go to the open problems. And then you can ask me your questions. Maybe the last part was a bit like confusing a bit, but okay. So one open problem that's immediate from even this talk is that there is a gap between the upper and lower bounds in the O tilde regime. That the upper bound has square root approximation and the lower bound is entropy monometric approximation. So what happens between here? Like, what is the right answer? And also, we looked at non-adaptive algorithms in this talk, and there's been a lot of work on completely adaptive algorithms. But what happens in the middle? What if I give you 2 rounds of adaptive queries? Right? That has been like it's completely unexplored. And so I think characterizing the power of R rounds of adaptivity is a very nice question. All right, so this is all I have for you today. Thank you so much for listening. And do we have any questions about the last part or anything else?
You don't have any result of that.
On like no.
What were the results for adaptive algorithms?
So for adaptive algorithms, you can get a 2.1 approximation or like very close to 2 in O tilde n queries. And if you want something like 1 minus epsilon approximation, like 1 plus whatever, 1 plus epsilon approximation, then you can do it in n to the 2 minus f of epsilon queries, and you need n to the 2 minus g of epsilon queries. Now these functions f and g are something, but yeah.
This 2 approximation algorithm, you enroll what it's actually doing is essentially really n rounds of the.
Yeah, it's a lot of rounds because what you're doing there is you're saying, there is if you fix some permutation on the edges, then now fix greedy matching, I will get estimated size matching. And to know if an edge is matched or not, you're asking its neighbors, are you matched? And then you're really doing this walk on the graph. So it can take up to n rounds. Now I don't know what happens that if I say I'm going to prove the walk and maybe to save on adaptivity, but I don't know what happens then. But yeah, like the way it's written, it's n rounds.
It's like some kind of range. Do you have any idea what curve you're expecting the race and the approximation and to the delta?
Yeah, good, right? So for an alpha approximation, initially when I was writing the paper, I thought maybe n square over alpha square, which is what we get from the upper bound, is the right answer. And turns out that the right answer for maximum matching when you have to output the element, n square over alpha square is actually the right answer. So, and this is irrespective of adaptivity. So if you have full adaptivity or no adaptivity, n square over alpha square is the right answer. But for matching size, now I think that maybe like the answer might even be somewhere in the middle. Like I don't know. Because the thing is, you don't have to do the same things you're doing for outputting the matching. You can look at some statistics or something to figure out something about the size, and maybe you can beat the square root and approximation that I showed you. So yeah, I don't like right now. I have no idea. Like, yeah, yeah. So,